Okay, good afternoon, everyone. I'm Stuart Mills, the CEO of DUNDEE. For those who aren't familiar with who DUNDEE is, we're the company right behind you at booth C22. I'll give a bit of background about us. You won't be surprised to hear that we're from Scotland, hence the accent. We're based in Dundee in Scotland, on the East Coast. We are leaders in spacecraft onboard data handling technology, specifically two technologies, space wire and space fiber. We are celebrating our 20th anniversary this year, so we were established in 2002. We are also celebrating 5 years being employee-owned. There may be some issues with the camera here. Are we good? Okay? Yeah, okay. Yes, we're employee-owned. We also have a wholly owned subsidiary based in Sant Cugat in Barcelona, which we imaginatively titled Star Barcelona. Being around for 20 years, we're well established. We're known across the industry. We supply to the world's space agencies, all the major space organizations and all the instrument manufacturers. We focus on developing technology. It's what we're good at. So we have highly technical staff. Many of our engineers have PhDs, and we outsource all of our manufacturing. So we take advantage of local suppliers wherever we can. And we've won lots of awards over the years for our work. In 2014, we were Scottish Business of the Year for companies with less than 25 employees. We've won a few local business awards. This is a photo of some of our team collecting a local business award just before the pandemic hit. We license our technology, and it's used in chip designs from the likes of Atmel, who are now Microchip, and it's used by many organizations and FPGAs licensed directly from us. It's used in spacecraft from all over the world. We also sell test and development products, so things to test out space wire and space fiber devices to interface to a spacecraft network. And we provide software, all the support and documentation that you need. So we've got some examples on the right-hand side. You can see some of the software running away. So that's a very brief and quick background on what we do. Before getting on to what space fiber is, I want to speak about its predecessor, space wire, which is a technology that's used all across the world by many organizations. It's an onboard data handling network, so it typically connects together the data handling elements of a spacecraft, from the instruments that collect the data down to the downlink that sends it back to Earth and everything in between. The spacewire standard was published by the ECSS, ESA's standardization body, in 2003. It was written as a collaborative effort by the European space industry and the world space industry, so there was involvement from people all over the world. But it was written by our chief technology officer, following inputs from all these people. It's now used in hundreds of spacecraft, so we have an example here of Bepi Colombo on its way to Mercury, and both the European and Japanese elements use spacewire. It's used in James Webb Space Telescope. It's used in all types of spacecraft as well. Wherever there's a need for data handling, spacewire is often used. And our chip technology is used in many of these spacecraft, as I already mentioned. The chip on the right-hand side is a spacewire 10x router, which is available from Microchip, which uses our IP. And this is a slide put together by ESA to show some of the agency spacecraft. You can see there James Webb, the Sentinel spacecraft that we've heard about earlier today, with some of the data being processed comes from Sentinel, and then the Astro H spacecraft from Japan. So spacewire is well adopted, but it's now 19 years old, and things move on. Everyone wants faster, they want more capabilities. So around 10 years ago, we started looking at the next generation of spacewire, and that's where space fiber came about. Initially, we were focused on fiber optic, so higher speed, we thought fiber optic, but we can also do space fiber over electrical. So most of the initial installations of space fiber are actually electrical copper cable, and we can go up to 5 meters at 2.5 gigabits per second with space fiber over electrical, or over 100 meters with fiber optics. But both the electrical and fiber optic versions of space fiber are much lighter than space wire cables, so there's a huge mass saving by switching to space fiber. Space wire typically runs at 200 megabits per second, around that figure. Space fiber, we can already do 6.25 gigabits per second per lane in current flight technology, and we actually have people going higher We have people who want to use 10 gigabits per second already per lane. But space fiber allows you to do much more. You can combine multiple lanes into a single link. So you can use bandwidth aggregation to increase the speed just by adding more lanes. So the example here, we've got a quad lane at 6.25 gigabits per second, gives a total link speed of 25 gigabits per second. And you can go up to 16 lanes. So there's a huge potential to go much faster, not only by increasing the lane speed, but by combining multiple lanes. The multi-lane capability also offers lots of other advantages. It can be used for redundancy. So if one lane fails, you can switch to a hot or cold spare, for example. And there's also support for asymmetric traffic. So you might have data going in one direction where you want to take advantage of lots of lanes, but only control signals coming in the opposite direction, so you just want one lane that's bidirectional. And it has lots of fault detection capabilities, so it's important on a spacecraft to be able to recover from a fault very quickly. And with space fiber, we can detect an error at the link level and recover from that within a couple of microseconds. So it's very good at coping with errors and correcting them. And as I mentioned, you can use multi-lanes to support graceful degradation. It has lots of quality of service mechanisms too, so you can have up to 32 virtual channels on a single link. So you can have virtual streams of data combined on a single link, and they're completely independent. And that can be used for lots of different purposes. So you can prioritize the traffic over one virtual channel in preference over another. You can reserve bandwidth on a virtual channel, so you might have control traffic that you want to schedule, for example, that has to get to its destination within a certain bounded period. And you can do that with one virtual channel while another is being used for data, which is being sent asynchronously, for example. So it can be used to combine deterministic data delivery and sort of asymmetric data, asynchronous data at any point. And the virtual channel concept can be used to create virtual networks. So you can combine multiple networks over a single physical network, and they act independently. That's very similar to having multiple space wire networks on a single physical space fiber network. There's also other features that were requested which aren't present in SpaceWire. So we have low latency broadcast messages, which can be used for time distribution. You can synchronize different devices. You can signal when there's an error. You can signal notifications. And the low latency mechanism means that it gets to its destination very quickly in a bounded time period as well. And despite all these capabilities, it's also designed for space. So it's designed to be as small as possible and fit on just a corner of an FPGA. So modern day FPGA, it's 1 or 2%. And it's also designed to be backwards compatible with space wire. So the packet level of space fiber is identical to space wire, which makes it very easy to bridge from a space wire device onto a space fiber network. So you can carry that space wire data from your star tracker, for example, and easily bridge it onto a space fiber network. So there's no change to the hardware, and the device itself doesn't know it's actually running on a space fiber network. So I've spoken for quite a bit. Here's an example of some of our software demonstrating these mechanisms. So my colleague Stephen put together this video of our Star Ultra PCIe board. He's going to bring up some statistics window, which will show the data being transmitted from a couple of virtual channels. So we've got the device in a loopback configuration, 2 ports connected together. And he has 2 virtual channels that he's going to transmit data on, virtual channel 1 and virtual channel 2. So he starts transmitting on virtual channel 1, and you can see the data rate there goes up to the maximum. It's taken advantage of all the bandwidth available. It's got 96% of the bandwidth reserved for that virtual channel. In fact, I think it has 86%, but it's taken use of all the bandwidth it can because it's sending more data than it's allowed, or it has reserved for it. Now, he's transmitting on a second virtual channel, and you can see the yellow virtual channel 2 is getting about half the bandwidth that's available. They're both scheduled to take 86% of the bandwidth, so they're taking advantage of what's available to them and sharing it between the two. But you can also then view that traffic, so we have different views of the data. He's going to record the traffic going over the link. Stephen's very slow with his mouse. And then we have different views of the data. So we've got a frame view, word view, packet view. This is the word view that's on display, and he's about to go to the packet view and then the frame view. So you can see there the two virtual channels are sharing the bandwidth equally. You've got about half on virtual channel 1, half on virtual channel 2, and those frames are interleaved between the two channels completely transparently to the end software. The data is being interleaved across the channel. Next, he's going to open the controller application and actually change the priority of the data of one of the virtual channels. So this controller application allows you to change priority, reserve bandwidth for virtual channels, and give time slots. So then you can schedule traffic within specific time slots. And what he's going to do is set the priority of virtual channel 2, I think, to be higher. And by higher, I mean lower. So a higher priority 1 is 1. The highest priority is 1. Come on, Stephen. Okay, so it's virtual channel 1. He's going to increase the priority. He's increasing that to 1. When he applies the change, we see now the pink line, virtual channel 1, is taking advantage of 86% of the bandwidth because that's what's reserved for it. And virtual channel 2 takes advantage of what's left over. So you can see that you can use this mechanism to prioritize traffic and ensure that the data that you want to get to its destination gets there. So that's a very brief overview of space fiber. Its current status: the standard was published in 2019. Again, Star Dundee and the University of Dundee worked on the standard with the international space community, but we very much led the research and development that led to space fiber. It's published again by the ECSS. We have IP cores available, single lane and multi-lane interfaces, single lane and multi-lane routers. There's several ASICs in development using our IP. The RC64 available from Ramon Space has our space fiber interfaces, 12 space fiber interfaces on it. There are a few demonstration missions. This one here is OPSAT. That's the Ramon Space chip above it. And there are lots more across the world currently implementing space fiber. There should be many launching in the next few months and next couple of years. We have several test and development products. We have a Starfire Mark III, which has 2 space fiber interfaces, 2 single-lane space fiber interfaces, and 2 space wire ports, and then a USB 3 interface to the PC. We have the card that I was just demonstrating there, the Star Ultra PCIe, which is a PCI Express interface to the PC and 2 quad-lane space fiber interfaces. And that can run at 6.25 gigabits per second per lane, so 25 gigabits per second per link. And we have an FMC board as well, which has both space wire and space fiber interfaces, which can be used to interface to an FPGA development board, for example, if you want to test out IP and develop for a device being used on a spacecraft. We have a Horizon 2020 project called HiSide, where we're working with partners across Europe to demonstrate a high-performance onboard data chain from instrument to ground. So everything from the cameras generating the data down to the downlink. And we're involved in several aspects of that. One of those is the space fiber routing switch, which sits in the middle of the network, which we've called Star Tiger. That's the box on the right. It's about 10 centimeters squared. It has 10 space fiber ports, with each port running at link speeds of up to 12.5 gigabits per second, given a user data rate of 10 gigabits per second when you accommodate the space fiber overhead, the protocol overhead. With the 10 ports at 10 gigabits per second in both directions, that gives a total throughput of 200 gigabits per second through that router. So it's a very powerful device. And it's designed for space flight. It doesn't use flight components completely. It uses some EM flight parts or industrial equivalents, but it's designed with flight in mind. and that'll be getting tested later this year. This is the network that's been built. We've got the routing switch developed by us, a camera developed by us, an instrument simulator and control computer, which is being run on PC with Star Ultra cards, mass memory from Airbus and ourselves, a data compressor from Airbus in France, the HBDP data processor from ISD in Greece, the RF downlink from TSAT with the solid-state power amplifier from Erzia, and an optical downlink from DLR. So that's the entire network that we'll be demonstrating later this year with some great partners, and that's all running at 10 gigabits per second per link. So it's a very high-speed demonstration of what's possible with space fiber. To summarize, we've got a high-throughput network capable of 6.25 gigabits per second at the moment, and will get faster. You can combine that into as many as 16 lanes per link, given 100 gigabits per second per link in current flight technology. It offers high reliability. It can do deterministic delivery. It can detect and correct errors within a couple of microseconds, and it can recover from those errors without loss of information. And it offers high availability, so the multi-lane capability can be used for many purposes to offer higher speed and also to ensure you have a hot or cold redundant spare available. Thank you everyone for listening. I'd be happy to answer questions, or if you'd like to speak to us at our stand, it's right behind you. And thank you for your attention.